Yes. Students, are you able to see the PPT? Students, are you able to see the PPT?
Yes, sir.
Okay. Okay, already we discussed this. Few conductance we already discussed. Hybrid pi conductance. I will just recall this. First one is transistor conductance, represented by GM. You can see here. This is I. And here we are showing this B dash, which is virtual terminal, and the resistance between base and B dash is RBB dash. This base is spreading resistance. Now the voltage between B dash and E, this we are representing by VB dash E, and as well as here between base and emitter we also represent it by VE, voltage between VE, emitter voltage. Now we know that in active region the collector current is given by this formula. Already we know IC is equal to alpha IE. See, already we know what is alpha. Alpha is IC by IE, right? So IC is equal to alpha IE, and this ICO is the reverse saturation current, because collector and base junction is reverse biased. That's why in that reverse bias you will find this leakage current also. So alpha is current amplification factor, ICO is the leakage current when emitter is open. Now the current generator in hybrid pi model is given by GM VB dash E. Current generator, you can see here, I will show you this, right? So this is represented by GM, which is transistor conductance multiplied by VB dash E. Okay. So it is represented by GM VB dash E. The transconductance GM is given by, so conductance is current by voltage. So here it is IC by VB dash E, right? So del IC by del VB dash E, or GM is equal to, in place of IC, so now in place of this IC, I will write this expression, right? So del alpha IE plus ICO by del VE. Now, so simply I have splitted this expression as del alpha IE by del VB dash E plus del ICO by VB dash E. So in this way. right? This expression. And here we know that this ICO, this is leakage current and this is constant, right? It is temperature dependent, and at particular temperature its value will remain constant. So since ICO is constant, therefore del ICO by del VE term will become 0. So now we have GM is equal to, only this term is there, del alpha IE by del VB dash E. Alpha is again a constant, so that I have taken outside here. This is alpha del I by del VE. This is my expression number 2. So here what I did, VB dash E is replaced by VE, right? Because you can see here in this diagram, VB dash E and VE are same. Now the emitter diode resistance is represented by RE. Emitter diode. See, in NPN transistor, if you see, this is NPN, right? Emitter, base, collector. So now you see between emitter and base, one diode is formed here, right? So the resistance of this emitter diode is RE, and it is given by del VE by del IE, right? Because here you see you will have the current IE, and the voltage between emitter and base will be VE. This is the voltage. So RE is del VE by del IE. Putting the value of RE from 3 in 2. This is the 3 and this is the 2. So what we will get? We will get alpha So here it is IE by VE. So IE by VE I have written in denominator as del VE by del IE. So alpha is equal to RE. Right? This is equation number 4. So we got this GM is equal to alpha by RE. Now the RE of diode, of any diode, the resistance is also given as VT by IE. Here VT is the thermal voltage whose value is 26 millivolt. VT is 26 millivolt. So now equation 4 can be written as, what is our equation 4? This. VT by IE. So GM is equal to alpha IE by VT. This expression will come. Now alpha IE in numerator. What I will do? From this expression number 1, I will take the value of alpha IE as IC minus ICO and I will put there. So I will get GM is equal to, in place of alpha IE, I have written IC minus ICO by BT. Now if you see the IC value and ICO, ICO is leakage current. So leakage current is in microampere, very small, whereas IC is in milliampere, right? So IC is greater than ICO. So you can neglect ICO, this current. So since IC is greater than the ICO, and ICO can be neglected. So what we will get? GM is equal to IC by BT. So this is the expression which we will use for conductance, transistor conductance. Now we see the input conductance here. Input conductance GB dash E. So this input conductance GB dash E can also be written as 1 by R B dash E, right? This input conductance. right? So see, this is figure 2. So in figure 2, figure 2 shows the hybrid pi model at low frequency. See, if you see the hybrid pi model, then you will find the model like this. This is the hybrid pi model, right? This is hybrid pi model. So here we have three capacitances CC, CE. Two capacitances are there. These capacitances are formed due to the internal architecture of a transistor. So at low frequency, when frequency is less, at that time the capacitance acts as short circuit. No, see, Xc is equal to 1 by 2 pi Fc. So if frequency is small, then capacitive reactance is big, right? So what we can do in that case, these capacitance will act as open circuit, right? So you can neglect these capacitances at a low frequency. So if you neglect so this figure number 2 shows the hybrid pi model at low frequency where all capacitances are negligible. So only thing what I have done, I have removed the capacitances because they are acting as an open circuit. So this is a figure, right? Here, this is B, this is emitter, base is spreading resistor, and B dash E, resistance between B dash virtual terminal to emitter. Then this is R B dash C, right? This is also called as feedback resistance here. Then here this is current generator GM VB dash E, and this is resistance between C and E. This is IC. So exactly same hybrid pi model I have drawn here. Only thing is I have removed the capacitances, right? Now figure 3 shows the same transistor using H parameter equivalent circuit. So now if you want to draw the H parameter of this transistor where we are operating it at low frequency, then what is the H parameter model? This is the H parameter model. This is B, here E, this is HIE, right? And HIE means input resistance, HRE reverse voltage gain, and VCE. So this is voltage source, and here there is a dependent current source, HFE multiplied by IB, where FE is the forward current gain, and HOE. So this is the H parameter equivalent model, right, of a transistor which is operating at low frequency. This is my figure number 3. Now see, we if you see the transistor, NPN transistor, it is like this. This is emitter, base, collector. We know that the doping, high doping is there in emitter, high doping. And in collector, with respect to emitter, it is low doping. right? If high doping, then its conductance will be more, or in terms of resistance, if you will see its resistance, I write it as B dash E is small, because doping is more means charge carriers are more, so conductivity is more, so the resistance is small. Whereas in collector, if you compare, then in collector the doping of the charge carriers is less. So if doping is less, so conductance will be less, so resistance will be more. So R B dash C is more. So typical values are taken here, or simply you can see here R B dash C is greater than R B dash E, right? R, this is this, here we have point B dash, right? And here there is a resistance, and here there is a resistance. This resistance is R B dash E, and this resistance is R B dash C. So R B dash C is very much larger than R B dash E, right? And its typical value is R B dash C is 4 mega ohm and R B dash is 1 kilo ohm. So huge difference is there. Now, if this is the case, then R B dash E is here and R B dash C is here. So this is around 4 mega ohm, and this is around 1 kilo ohm. So this IB is flowing, IB is coming here. At this junction, it will try to move towards this side and this side. So since R B dash C is very high, so very small current will go towards this side, right? And all the current will flow towards R B dash E, right? Because its value is small. So same thing I have written here. Since R B dash C is greater than R B dash E, therefore IB flows through R B dash E, right? And if IB flows through RB dash E, this means through here our IB is flowing. It will be IB multiplied by RB dash E, right? Same thing is written there. VB dash E is equal to IB multiplied by RB dash E, right? Now, since IC is equal to GM VB dash V dash E, so here this. So this is current generator, right? So IC is equal to GM, and in place of VB dash E, I will put IB RB dash E, this value, right? Now HFE, what is HFE? HFE is current gain. So current gain means output current by input current. Output current is IC and input current is I. Oh. Okay, I was disconnected. Okay, so we'll continue. Right, we were discussing this slide. Right, so HFE is IC by IB. Now putting the value of IC from 2 in above equation. So in 2 IC is equal to this, right? So HFE is equal to GM IB RB dash E divided by IB, right? So IB and IB will be cancelled out and you will get HFE is equal to GM RB dash E, or RB dash E will be HFE by GM, right? And this is our expression number 3. And from here, see what we were calculating. We were calculating the inductance, right? GB dash E, and GB dash E already I told you it is 1 by R B dash E, right? So RB dash E we have calculated. It is this. So what is GB dash E? It is the reverse of expression number 3. So it is GM by HFE. So in this way we can find the input conductance, right? So how we calculated? First, you draw the hybrid pi model at low frequency. You remove the capacitances. Then you draw the equivalent H parameter model, right? Now, since the value of RB dash C is greater than RB dash E, therefore full IB will flow through RB dash E, right? So here this will be open circuit because its value is very high. So full IB current will flow through this. So the voltage across this resistor RB dash E will be VB dash E, right? So I have written here VB dash E is IB IB into RB dash E. Now since IC here, IC is this current generator. So here we have written this IC is GM B dash E, and in place of V B dash E, I put this value. So this is my equation number 2 will come, right? And HFE, we know that it is output current by input current, that is IC by IB, right? So IC value, I will bring this IC value. So HFE will be this. IB will be cancelled out. So HFE will be this, right? And RB dash E will be this expression, and GB dash E is the reverse of expression number 3. In this way, we can do this. Now we will see the feedback conductance. So what is the feedback conductance? So if you see the H parameter model, so this resistance is a feedback resistance, right? Because it is connected from the collector terminal, which is output terminal, and B dash, right? So this is the feedback resistance. So its conductance, we want to find the conductance, feedback conductance, right? So feedback conductance is GB dash C, or it can also be written as 1 by R B dash C, right? So now from figure 2, HRE. What do you mean by HRE? It is reverse voltage gain. Reverse voltage gain. So HRE is input voltage by output voltage. Input voltage is VB dash E and output voltage is VCE. So see here this figure 2. I am talking about this figure. Okay, here I will draw. This is VCE. Right. So HRE is input voltage is VB dash E and output voltage is VCE. This. And this is equal to this expression. So how this expression number 1 has come here, that I would like to just explain to you. See, if you draw that figure, okay, here itself I will tell you. In this figure, you can see this figure is like this. See, this is your RCE, this resistor, and here this is a current source. This I have drawn like this. This is your GM V B dash E, and see this IC current is coming, and it is divided in 3 parts. One, it is coming here. Second, it is coming here, and third part is coming there, like this, and this. Suppose this is I. This is my I, and here IC is coming. This is IC. So here we have I in this loop, and it is flowing like this, right? So we see, right? So now you concentrate in this, loop, in this part, right? In this part you concentrate. So what we can write? We can write, if we apply KVL in this loop, V C minus I R B dash C minus I R B dash E is equal to 0 in this loop, right? And from here I will find out the expression of I. So I will be V C divided by R B dash. This is IC. This is I, right? Now you see this I is also flowing in this resistance RB dash E. So V B dash E will be the voltage, this V dash E, it is the voltage divided by R V dash E. V dash E is equal to VCE R B dash E divided by R B dash C plus R B dash E. This is the value of VBE, right? So now you come to this reverse voltage gain expression. HRE is equal to VB dash E by VCE, right? So what I will do in place of VBE, I will write that expression which just now I have calculated, and that was VCE R B dash E divided by R B dash E plus R B dash C. This is the expression of VB dash E. Just now we have calculated and divided by VCE. So we will get here VCE, and this VCE and this VCE is cancelled out. So what we got? We got this RB dash E divided by RB dash E plus RB dash C, right? So the real calculation came from here, which just now I explained. Okay. Right. So this is my expression number 1. Or I will just simplify this HRE multiplied by this RB dash E plus HRE multiplied by is equal to RB dash E. Or I will bring it in this term HRE into RB dash C is equal to R dash E minus B dash E. So this term I brought this side. B dash E common. Now see HRE smaller quantity. A voltage gain is high quantity, but reverse voltage gain is very small quantity, right? So since HRE is less than 1, right? So here 1 minus HRE. HRE is very small quantity. So you can neglect HRE term here. So what we got? We got this expression RB dash E. This means this we have neglected total. This is equal to HRE RB dash C, right? And this I have written now in terms of conductance. RB dash E, you can write it as 1 by GB dash E, HRE by GB dash C. RB dash C I have written in this way. So from here I will get the expression GB dash C, which is the feedback conductance, is equal to GB dash E, which is the input conductance multiplied by HRE. This expression I got. So this is the expression of feedback conductance. Okay. Now I will see. We will discuss another conductance, that is the output conductance, right? Output conductance is written as GCE, or it can also be written as 1 by RCE. So if you recall, when we calculate during the H parameter or during the Darlington pair, when we calculated the output resistance, output admittance, then we made the open circuit at the input side, right? So same thing we will follow with input open circuit. The conductance is defined as HOE, right? If you recall, while calculating HOE, we make the input side open circuit. So open circuit means IB is 0. There is no base current. Base current is 0. So in that case, if you write the IC expression, then you can see here this IB in this figure 2. IB you make 0. Then IC. IC is, see, some current is coming here. I call it I1. This is my I2. And this is my I3, which is flowing like this, right? So IC, and here we have this voltage VCE. So IC is equal to VCE divided by RE plus this I2 GMV V dash E plus considering these two resistances, right? So IC will be so here I can write from figure 2. From figure 2. So IC is equal to VCE by RCE, and this generator, current generator GMVB dash E, and VCE by RB dash and RB dash C plus RB dash E, considering two resistances, right? Now HRE, reverse voltage gain, is VB dash E divided by VCE, or VBE is equal to HRE multiplied by VCE. From here only, we have written this expression in terms of VB dash E. This is my expression number 2. Now putting the value of VB dash E from 2 in 1. So in this one, I will put the value of VBE here. I will replace this. So what I will get, IC is equal to VCE by RCE. It is same. This is also same, and here I have written GM HRE VCE. Then IC is equal to, in all these three terms, right hand side, all these three terms, VCE is common, so that I have taken out common. So 1 by RCE, 1 by RB dash C plus 1 by RB dash E plus GM HRE. This expression will come. Now, see, HOE is output admittance. So admittance, output admittance means IC by VCE. This is HOE, output admittance. So here is IC, here VCE. So I will bring VCE towards left side. So this is my expression number 3 now. IC by VCE, which is your HOE, is this. Already we discussed that RB dash C is greater than RB dash E, right? Where RB dash C is around 4 mega ohm and RB dash E is 1 kilo ohm. So we can neglect this RB dash E here. So in this denominator, we can neglect RB dash E. So our expression will be HOE is equal to 1 by RCE by 1 by RB dash C. Only keep this, neglect this, plus GM HRE. This is my expression number 4. Now we know the input conductance GB dash E. What is the expression of GB dash E? We calculated input conductance GB dash E. This GB dash E is GM by HFE. Same I have taken there. This GM by HFE, and I given the name to this number 5, and the feedback conductance GB dash C. What we calculated? This GB dash C is GB dash E multiplied by HRE, right? So this is HRE. You can correct in your notes also. It looks like F, but it is HRE, right? This is HRE. So now what we will do? From this, I will take the value of GM and I will put it here, right? So putting the value of GM is equal to GB dash E HFE from 5, and from expression 6, I will find out the value of HRE, as HRE will be GB dash C by GB dash E. So this value I will put here. These two values I will put in expression number 4. So what I will get now? HOE is equal to this is same, and here HFE GB dash E, which is GM, and HRE is GB dash C by GB dash E. GB dash E and GB dash E will be cancelled out, right? These two will be cancelled out, and what we will get? HOE is equal to, see, 1 by RCE is GCE. 1 by RB dash C is GB dash C, feedback conductance. GB dash C, HFE GB dash C. And what we have to calculate? We have to calculate the output conductance GCE. So I will bring this expression in terms of GCE. So GCE is equal to HOE minus GB dash C minus HFE GB dash C, or HOE, the output conductance is HOE minus, in these two terms, I will take GB dash C common. So this 1 plus HFE, right? So this is the expression. This is the expression for out. I will stop here.